Welcome back to CS201 Walkthroughs. My name is Lukash, and today we're going to be talking about converting between binary, decimal, and hexadecimal. I had a little bit of time after class, so we're just going to kind of run through these functions. I know that they can be a little confusing. It's going to feel like I'm showing you magic. You don't have to worry about the procedures too much and why they work. Just trust that these procedures do work, and if you really want to, you can watch it a couple times and understand why they work. So, bin to dec, we're taking a binary to decimal number. I'm just going to rewrite this binary number as 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2 plus 0 times 2 to the 3 plus 1 times 2 to the 4. If this is confusing to you, then go back and watch the last video about these representations. But if you understand this, then maybe you'll understand if I keep rewriting this number one more time as 0 times 2 times 0 plus 2 times 1. Messing up my plus and multiply now. 1 plus 2 times 1 plus 2 times 0 plus 2 times 1. Okay. I'm going to show you how this makes sense. Don't worry. This maps to that. This 1 times 2 to the 4. This 0 times 2 to the 3 is here. This 1 times 2 to the 2 is here. This 1 times 2 to the 1 is here. And this 0 is here. The reason this works is because this one over here, if you think about it, ends up getting multiplied by 2 4 times. You can stare at this for a little bit if it doesn't make sense to you yet. But this helps us define a recursive procedure. So for bin to dec, I can say something like, if it is, we need a base case, which I'll let you figure out. Probably be something like when I've gone all the way through my number. And then a recursive case will say something like, add last digit, or I'll do last digit plus 2 times bin to dec rest of num. And by rest of num, I mean everything except for the last digit. So that's what I did here. I can write it as 0 plus 2 times bin to dec 1011. And this we'll call 1 plus bin to dec 101. And this will keep going. I hope you understand why I'm multiplying by 2 each time. 1 plus 2 times bin to dec 101. So as long as I'm increasing the multiplicative factor by 2 each time, that will fit with this numeric representation. And this helps me just define a recursive procedure that works for this. Okay. And if you think about it, there are very easy ways to get the last digit of a number, perhaps using remainder, and to get the rest of a number using something like divide. I'm going to erase this, so pause if you still need it. To do the reverse, I'm going to show you sort of this weird magic trick that is very clearly recursive. You don't have to worry too much about why it works. If you do, you can stare at it, but here we go. I'm going to take 22. I'm going to divide and floor it. So actually, I'm going to write this a little differently. I have 22 over here. I'm going to divide and floor. Divide by 2 and floor. So it goes to 11, which goes to 5.5, which floors 5, which goes to 2, which goes to 1. Now I'm going to ask if it's even, put a 0. If it's odd, put a 1. So this will go to 0, 1, 1, 0, 1. And this is equal to our binary representation of 22. A little bit strange to think about, but very easy to implement in code, right? I can just say divide by 2, or maybe I'll write it up differently. I'll say in Dec to bin, we're just going to divide by 2 and floor until at 1 or 0, depending on your base case. Each time put 1 if odd, 0 if even. If you want a hint about why this works, you look at 22 is even, and any number that's even has a 0 as its last digit in binary, because there are no 1s. A 1 would make it odd. This kind of applies to every single digit when you keep dividing by 2. But I'll leave that for someone else to explain. I'll erase this so I can move on. Pause if you need. These two are going to look a little bit similar. Again, if you don't know what these letters are or you're confused about the representation, please watch the last video in which I specifically describe that. But otherwise, we can represent 2AF as F plus 16 times A plus 16 times 2. So this is the same as 15 plus 16 times 10 plus 16 times 2, which you know will give us 687. Maybe I'll show it to you. I'll say 15 plus 16 times 2 is 32, plus 10 is 42. I can get out my calculator. Well, this is 420 plus 6 times 42 is 240 plus 12 gives us 72 plus 15 equals 687. Okay. And again, it's the same sort of recursive procedure we did with bin to Dec, just we're replacing the 2's with 16ths. Okay, I'm going to erase it. Over here for Dec to hex, we'll do something similar to what we did in Dec to bin. We'll say, take 687. Oh man, I would need a calculator for this. Well, divide it by 16. So I did some really quick math to figure out that 687 divided by 16 is 42 with a remainder of 15. So I'll just say this goes to 42. I'm going to put 15 down here. So I didn't explain too much what we were doing over here, but when I said even becomes a 0 and odd becomes a 1, what we were actually doing was taking the remainder when divided by 2. So 0, the remainder, whenever you divide an even number by 2, the remainder will be 0. Whenever you divide an odd number by 2, the remainder will be 1. So here I'm doing the same thing. I'm just taking the remainder when you divide by 16. So here the remainder of this number divided by 16 is 15. So I'm going to put that down here. Here I got 42. I'm going to divide by 16 again. I'm going to get 2 with a, here I'll write remainder 15. Here I'll write remainder 10 because 2 times 16 equals 32 and 42 minus 32 equals 10. So here I'm going to put 10. And then I'm left with 2. So 2, 10, 15 is the same as 2AF, what we started with. Again, I know this process is confusing, but I'll describe it more generally. In Dec to hex, until our number, num, less than 16, or I guess until our number, the way I would write this, my base case, it would be equals 1, because I would turn this into 1 with a remainder of 2. When I divide this by 16, it's 0 copies with a remainder of 2. Or sorry, oh yeah, this would turn into 0, never mind. So 1 or 0, same base case as before, until num equals 1 or 0, divide by 16, put remainder into list. So this shouldn't be actually that difficult, or I guess divide by 16 and floor, in case it doesn't exactly fit, and put the remainder of that division into a list. This is a simple recursive procedure. If you tried to do something like figure out the highest power, my initial approach when thinking about this question and about this over here is, I have a number like 1, 4, 5, 6, whatever. I have to start by finding the highest power of 2 that can fit in this. And then that's something like 2 to the, I don't know, maybe 10. And then I'm like, okay, 1024, take that out, and I get, 432, and then take the highest power of 2 that'll fit in this, and that's what, 256, and then subtract that out. You don't need to do that. This procedure here and the one I described previously will make this a lot easier to code for you, even though they're not the intuitive way of doing it. I hope that has given you some help for these unusually tough questions, kind of conceptually, and putting them into code. If you have trouble, come to office hours, post on the Piazza, email the CS201 help email, or even comment on this video. Thanks for watching, and happy coding.